And the first talk will be by Dinakaran.
So this is a work which is sort of close to completion. This is work with Arpita and her student Pratik, and also with folks at IBM, Nitin and her manager Pankaj. So this is a work on thinking about distributed proof generation in zero-knowledge proof protocols. So to give a brief recap of the definitions, typically all the zero-knowledge protocols considered till now, most of the time they talk about a single prover who has a witness, and there is a statement X which the prover and the verifier interact with each other to check whether the instance and the witness they satisfy this deterministic algorithm. So that's one way of expressing it. And okay, and this protocol should satisfy three properties. One is the property of correctness, that if this algorithm is satisfied and if the prover has witness which satisfies this algorithm, then the verifier will always accept the proof. That's for perfect completeness. And soundness says that informally it says that if the prover does not have a witness which satisfies this algorithm, then the verifier will not accept with overwhelming probability. And the property of zero knowledge says that during this process of the prover convincing the verifier does not learn any information about the witness W than what he has before the protocol begins. So this is when there is a single prover who has all the witness with itself. In our work, we study the notion where there are multiple provers. They have witnesses either say partitioned, or to be more clear, they can be even say secret shared among themselves. And what we are trying to see is, in this setting, how do we construct a zero knowledge proof protocol? And to recap the definitions, the completeness definition is similar to before, where if the provers together they have a witness which satisfies the same algorithm M, then the verifier will accept always for perfect correctness. The soundness is slightly modified. Soundness is always from the view of the verifier, even in single prover zero knowledge, and we are just modifying it to say that the verifier, if the provers do not have a witness satisfying this protocol, it can be of any form, the verifier is going to reject almost all the time if provers are not satisfying this. The witness is not satisfied. The thing will be which differs slightly more is the zero knowledge property, where we say that the verifier should not learn anything about the witnesses of a subset of provers even after it colludes with the remaining provers. So the definition of zero knowledge, at least from it differs from a single prover zero knowledge protocol in this way. Okay, so like just to motivate this, it can be in multiple scenarios. For example, a very simple use case we always start with is if there are multiple businessmen and they have their bank account balance to be private, and they want to show to a loan provider that they together have a total balance which is greater than the amount the loan provider wants from the people who it's giving the loan to. So that's one simple thing we start with. And then in cryptocurrencies, it could be that there are multiple, say in Bitcoin, there are multiple users and they want to create a transaction using coins from each of them, and they say want to mint a coin which combines all the coins from multiple users. So in that's another use case where it could do it. And in a typical supply chain, it could be that you want to prove something about a quality of product from multiple producers in a locality. You want to show like a single proof saying that this locality always produces products of this quality, and the product comes from multiple producers. So how do you produce a joint proof without the provers revealing without the producers revealing their business information to their competitors? So in this work, we just study this notion of zero knowledge and then think about different definitional extensions and prove simple theorems about it in terms of definition. And Then we give a construction for a zero knowledge protocol. We first study the existing zero knowledge protocol and how they transfer to this setting of distributed proof generation, and then we propose a protocol which sort of lies in the middle in terms of the single proof protocol also, but in terms of distributed proof generation we show it's like better among all the prior art. So just to summarize the result in one slide or 2 slides, we have 2 protocols. One gives a proof size of, the single proof version gives a proof size of n to the 1 by c, where n is the number of gates in the circuit for some arbitrary constant c, and the prover complexity is n log n. And also the verifier complexity, it's a protocol based on public key operations, and the total number of total asymptotic complexity of verifier is O of n, but the public key operation is slightly less, n to the 1 by c. And then we have a second version where the proof size remains the same, but we further reduce the number of public key operations that the verifier use, and potentially also we can batch the verifier complexity to be like lesser. So that's it. Yeah. Any questions?
Thanks, Dinakaran. The next talk will be by Chaya.
Okay, thank you. So let's begin. Most of the crypto we do is in the following setting, where we have sort of 2 parties. They have their own secrets, and we want to like design protocols which protects, say, an honest Alice against a dishonest Bob, or in certain other cases where we want to protect both of these honest parties against some third adversary. But what really happens in reality is Alice is being implemented by her computer, and Alice has to trust that her computer actually implements the protocol that she is supposed to. And the question is how much trust can she really place on her computer? And the motivation is very nicely summarized by this XKCD comic. We typically focus only on the bold line here and forget about this dotted line, which is where things tend to fail. And this is also seen in practice in widespread bugs, accidental or deliberate, I don't know, in cryptographic standards and software. We had the SSL vulnerability, the heartbeat bug, Apple go-to-fail, PRNG bug, and logjam attack, and many others. And this is actually NSA intercepting Cisco routers and doing I don't know what with it. And in fact, this is an excerpt from NSA's budget request, and let me just read it out. The enabling project actively engages the US and foreign IT industries to covertly influence and/or overtly leverage their commercial product designs. These design changes make the systems in question exploitable with foreknowledge of the modification. To the consumer and other adversaries, however, the system's security remains intact. And this was indeed confirmed after Snowden revelations, which told us about these massive data collection programs like Prism and Bullrun, and backdoors installed by the NSA and perhaps by other agencies. And later it was also revealed that a lot of Juniper devices deployed were indeed backdoored that used the dually CDRBG random number generator. So what do we want to do? We really want to design protocols in the real world where the computer is not really trusted to implement what we really wanted to implement. For instance, Bob could ask, what is Alice's password? And the computer could tell it, and then Bob could ask, oh, give me the credit number, please. And the computer could indeed give it to Bob, and Alice wouldn't know. So there has been some prior work in this kind of setting, starting from the work of Simmons from 1984 on subliminal channels, and the work on divertible protocols and kleptography of Young and Jung. And more recently, there has been work by Bellare and others on what is called algorithm substitution attacks, which looks at backdooring of symmetric key encryption schemes. And there is this work that is joined with Evgeny, Sasha, Ari, and Tom on backdoored PRGs, where we formalize this dually C PRNG attack and show both negative and positive results for backdoored pseudo-random generators. And both of these were sort of impossibility results in a strong sense. And there is this work by Noah and Ilya and a follow-up by Evgeny, Noah and Ilya on the reverse firewall framework, which shows us how to get around these impossibility results in what is called the reverse firewall framework. So in this work, we look at constructing cryptographic reverse firewalls for interactive proofs, and this is joint work with Bernardo Magri and Daniele Venturi. So let me just tell you a little bit about what this reverse firewall is. So we think of the firewall as sitting between Alice and the outside world, and what it's going to do is it's going to take messages from Alice and modify it before sending it to Bob. Takes messages from Bob and modifies these incoming messages before forwarding it to Alice. We want this firewall to be transparent, that we don't want Alice to know that there is a firewall sitting, and we don't want Alice to change what she does in the protocol. And importantly, we don't want Alice and the firewall to share any secrets. So the reverse firewall should not break the functionality of the underlying protocol, and the firewall is not trusted. So what we want is security even if the firewall is corrupt, and security even when the implementation is corrupt. So if the underlying protocol had a certain functionality, then we want the firewall to retain that functionality. So this is the functionality maintaining property of the reverse firewall. And in addition, if the if the underlying protocol satisfied some security notion in the presence of a dishonest Bob, then we want the firewall, the protocol with the firewall, to satisfy the same security notion even when this implementation is insecure. So this is the security notion of the protocol with the firewall. So in the work of the reverse firewall, in the two reverse firewall works, they gave a sort of very general positive result where they showed how to achieve generic secure two-party function evaluation in this reverse firewall framework. But they used very generic techniques like Yao's garbling, which means that any protocol has to be represented, the computation has to be represented as a circuit in order to construct a reverse firewall. And in the second work by Evgeny, Noah and Ilya, they showed more positive results, but the downside is that this firewall is not transparent, which means that not only does it increase the round complexity, it sort of changes the underlying protocol, where the very high level idea is to run the same protocol but in the encrypted domain. So this means that the underlying protocol is compiled into a completely different protocol, and now everything has to be sort of re-implemented. There has also been work on what is called subversion resistant NISC by Bellare et al. And a bunch of follow-up works. But here the setting is a little different in the sense that they think about security when the parameters are subverted and the implementation is still assumed to be trusted. So in this work, just to summarize it in one slide, we define what is possible and what is not for interactive proofs in this model where the implementation can be corrupt. And we show positive results for a wide class of protocols that we call malleable sigma protocols. And we construct efficient reverse firewalls for the prover in a very transparent way, so we don't have to actually re-implement any protocol. I'm going to stop here. Thank you.
Thank you, Chaya. The next talk will be by Ajit.
Good evening to all. I'm Ajit, and today I'll be talking on MPC meets ML, efficient privacy preserving machine learning techniques. Yeah, as you have seen in the last 3 days, secure multi-party computation, it enables a set of mutually distrusting parties to perform some joint computation on their inputs without revealing the inputs. So the goals are essentially correctness. That means at the end of the computation, parties should correctly compute the function, and privacy. That means nothing more than the function output and whatever they can compute using the function output and their own input. Other than that, nothing should be revealed. So in our work, we consider this MPC for small number of parties. It's mainly celebrated due to its efficiency and simplicity. And to be specific, in our line of works, we consider MPC with 3 or 4 parties. And the corruption scenario that we are considering is honest majority. That means for the case of 3 parties, at most 1 can be corrupted. Similarly, for the 4PC setting also, at most 1 party can be corrupted. And we consider the setting of this outsourced computation. So in this MPC for small number of parties, if there are a large number of parties who want to perform some computation, what we can do is the parties can choose a subset of parties, say like three parties, and they can, the whole population can distribute their data to this small number of parties, and they will perform the computation and give the result back to the parties. So this way we can actually solve the problem of a large MPC for a large number of parties to this MPC for small number of parties. Now coming to privacy preserving machine learning, I am going to explain with respect to machine learning inference, where there is a model owner, say Alice, and a client, say Bob, and they want to compute some ML algorithm. So Alice will provide the model parameters to the algorithm, Bob will provide his query, and the ML algorithm is computed and the result is given back to the Bob. So what about privacy? That is the issue over here. So for example, if the model owner is corrupt, then she is seeing the query in clear, okay, which violates the privacy of Bob. Similarly, for the case of a corrupt client, from his query and the result, he may be able to get some information about the model parameters which the model owner wants to hide. So how to solve this issue in a privacy preserving manner? And the answer is, what we are going to do is, we have MPC in one side and we have this ML algorithms on the other side, and what we want is the best of the both. We want to, this is where basically MPC meets ML. So in our work, what we are going to do is, we are going to instantiate the underlying ML algorithm using MPC techniques. So for instance, earlier there was model owner and Bob communicating to each other, but now there is a set of 3 servers. For the case of 3 parties, there is a set of 3 servers, and model owner provides the model parameters and client provides the query. So this model parameters as well as query, they are distributed to this set of 3 servers in such a way that not one server can learn about either model parameters or query in clear, okay. And the servers perform the computation and the output is reconstructed towards the, or sent towards the client. So a quick summary of our results. So these are some fancy names which we will see. Basically this is Astra, Flash, Blaze, Trident and Swift, which we will see. So coming to 3PC, in the setting of semi-honest setting, where parties are parties will follow the protocol steps correctly. So the earlier result of Araki et al. For the case of a 3PC multiplication, so here we are considering the cost of multiplication because that involves the majority of the communication in a protocol. So in the result of Araki et al. In 16, they provided a multiplication which requires parties to communicate 3 ring elements overall. And when it comes to dot product, so by dot product what I mean is the inner product of 2 vectors. So the dot product can be viewed as, if the vector length is say d, then the dot product can be viewed as a set of d multiplications, okay. In the semi-honest, the work of AB/3 showed how to achieve this dot product with a cost that is same as the cost of a single multiplication. So they also require a cost of just 3 elements. I forgot to mention, our protocols are actually cast in this pre-processing model. So by pre-processing, what we mean is, before the computation starts, the servers, they will jointly generate some correlated randomness. Using the correlated randomness, when the actual computation starts, they will make use of this correlated randomness to perform some fast computation. So our protocols are cast in the pre-processing model. So in the 3PC semi-honest setting, the works of Araki et al. As well as AB/3, they don't have anything in the pre-processing, but all the computation are happening in the online. So our first result is Astra, where we could shift essentially one element, or like 33% of the communication from pre-processing, from online to the pre-processing stage. And the same result holds for the dot product computation also. Now coming to the stronger security setting, where it's malicious in the 3-party case, the work of Araki et al. In 2017, they proposed a multiplication protocol which requires communication of 12 elements in the pre-processing and 9 elements in the online phase, and they provide a security of abort. So security with abort means parties can abort at any stage of the protocol. Okay, that's the weakest form of security. Then as you have seen in the last day's lectures, fairness means we have the guarantee that as long as adversary is getting the output, the honest parties will also get the output. And GOD means it's guaranteed output delivery. Whatever the adversary is doing, the honest parties are guaranteed to get the output. So the work of AB by 3 considered 3PC malicious case as well, and when they converted this multiplication to the case of dot product, the cost was directly proportional to the length of the vector. So in Astra we could basically trade off the pre-processing cost and reduce the online cost from 9 to 4, and we achieved the security notion of fairness. And the interesting result is, when it comes to dot product, it's not the online cost is not directly proportional to the number of multiplications in the underlying vector, but rather it is reduced from 9D to 2D plus 2. Then in our follow-up work, we could reduce this cost from 21 to 4, 21 and 4 to 3. So I will quickly summarize the results. And the dot product in the online phase, we could get a communication which is independent of the size of the vector. And in a follow-up work, we could improve the security from fairness to GOD by trading off the pre-processing cost by one element. And the dot product also, the pre-processing cost is slightly increased by a factor just one element, and the online cost is retained. Now I am just, due to lack of time, I am just going through the results. Yeah, so this is our results in a nutshell. Yes. No, this is basically. No, it's not about whether she is putting the correct parameters. I don't want to reveal my data to the model owner. So if I am asking to the model owner in clear, she will be seeing my query, right? I want to preserve the privacy for with respect to my query also. Yeah. Yeah, sure. I'm sorry, I couldn't hear.
Have you quantified how much leakage you have? Because, for example, if you compute regressions, if you compute it many times, you leak the parameters from the output of the computation.
Yes, in fact, there is a recent paper which is efficiently stealing the models from this computation. Yeah. So there they show this, means they are inherent to the underlying ML algorithm. Means if it is a linear regression which has say, which is working on vectors of d size, then after d plus 1 queries, all the model parameters will be leaked. So these are something which is not in the scope of our work, but the ML algorithm has to like improve for this one, for this kind of preventing these kind of leakages. Yeah, if linear regression is leaking the values after d queries, so better limit the queries to d. And in fact, we even thought of basically.
Yeah, you can say you can limit the number of queries, because then it doesn't make sense. Yes. Or add some differential privacy to increase the number of queries.
Yes, or in fact, after this limit of queries, you can basically retrain the model so that using the predictions that it already did, so that the model parameters are now fine tuned again. So that way.
But if the data is the same, the model will be very close to the previous one. So retraining will not save you much.
Yes, so you should limit the number of queries.
Yeah.
Yeah, I'll stop.
Thanks, Ajit. The last highlights talk will be by Shyam.
My name is Shyam. Thank you for this opportunity. This is a work that we did in TPP along with my advisor Srinivas Vivek. This is basically slightly different from all the talks that we have been hearing from the last 3-4 days. This is basically an FHE setting and an attack on an existing paper that was published recently. So this is actually in continuation with what Ajit was mentioning in terms of the computation on the cloud by a client. Basically, the whole idea here is that this is KNN is the K nearest neighbor algorithm that is fairly popular in the ML world, wherein a client having a large amount of data stores it onto the cloud, and then it can issue a query to basically make use of the server's computation power to obtain a function basically on the data that is stored. For example, here in this case, K is the K nearest neighbors, and K1 basically means if you have a point on XY plane, the nearest point to that given query point XY plane. This is a KNN is, I believe, a fairly, I'm not an ML expert, but I believe it is a fairly basic ML primitive. It is fairly popular. And the question is obviously what is the privacy of the outsourced data. Now, one solution was basically the ML solution that Ajit was mentioning. The other thing is to basically to encrypt the data such that it supports homomorphic operations, and then basically be able to be able to do computation homomorphically, thus preserving the privacy of the stored data in the cloud. So to this end, there was a paper in 2018 published in EDBT, which is basically, I believe, a fairly well-known conference on databases by some folks from IBM Research and then IIT Kharagpur people, and they basically have a solution which is based off of SHE, which is somewhat homomorphic encryption setting, in a two-party non-colluding federated setting, where they are actually they show that they can handle very large data, that is like basically 100K plus tuples of the data, and which is basically fairly much better than their immediate rivals as they claim in the paper. So the setting is basically a two-server non-colluding setting. In this case, for example, server A may be Azure and server B can be a cloud from AWS, and the client stores the data in encrypted form in server A, but then shares the secret key to server B, such that the client issues an encrypted query onto server A, such that server A is able to basically compute the required computation homomorphically. For example, if you are trying to get the Euclidean distance between the query points AQ, BQ and the data points AI, then it basically gets these values xi, x1, x2, x3 homomorphically, and homomorphically meaning the whole data is the whole results are encrypted, and it transforms this data using a d-degree polynomial. This d-degree polynomial is an integer polynomial and a monotonic polynomial, and these px1, px2, pxi are computed by server A, and it permutes the order of the PIs, sends it to server B, who then basically, since it has the secret key, can decrypt it and then obviously sort it fairly easily. The whole point here is that homomorphic sorting is a fairly slow process at this point in time, and therefore server B will be able to efficiently sort in the clear. Once it sorts, it computes the indices of the sorted values and sends the indices to A, and then A will be able to apply the reverse permutation of the indices and then send the results back to the client. So this is basically the setting that was presented by the KNN plus paper. So the adversary here is B, since it has the secret key, and the whole expectation is that the server B can only learn this ordering of the distances and nothing more. This is because the Px is a random monotonic integer polynomial of a degree d equals about 9 or 10, because further depths are hard to compute homomorphically, and the number of points are very, very large. As I mentioned, it's a huge amount of data, and the ranges of the x and the coefficients are known to both A and B, and then the server B obviously has the polynomial outputs. It is claimed that the server B can recover these values with basically a value which is very, very negligible. So now what we have shown in this paper is that we can actually recover the polynomial and the x values much more efficiently than what they claim in the paper. So their argument is that basically you have n plus d plus 1 variables and only n equations, and then it's very hard to recover the values. Now we are not aware of any technique in the past, in the previous works, which recover the polynomials given only the output values. Lagrange interpolation basically takes the xy values, it can take d plus 1 values and then recover a d degree polynomial. That I think everybody knows. We've been talking about it many times. So basically the whole point is that in the enumeration space in this case happens to be 2 power 160, and therefore the probability of recovering is a very, very small number. But in this case what will happen is that the polynomial, even if you get a polynomial, it will be basically a family of polynomials, which is basically p plus basically x plus c. So in our attack we actually show a method to, as I mentioned, to recover both the x values and the polynomial, which is basically given that the beta is bounded. So what we know is that the px1 and px2, as I mentioned, is what we know from server B, and we compute the difference of these two, which means that x2 minus x1 is actually a factor of px2 minus px1, and as a matter of fact, all factors of p of x2 minus p of x1 is actually a plausible solution for the x2 minus x1 value. Now what will happen is that it is possible that some of the pxi minus px1 can have a large number of divisors, in which case we will actually limit it to basically a psi value less than say 10, so that our enumeration space is basically 10 to the 9, which is 2 to the 30, which is far less than what they claim in the paper. Yeah, I'll be done in 2 minutes. But then the whole point is that x1 is basically a free variable, because of which we will actually have to enumerate all the values of x1 starting from 0 to 2 to the power beta, which we do. And then once we are able to do that, we use Lagrange interpolation to be able to compute the polynomial and then apply the same polynomial to see if actually it satisfies all the other values, as well as see that the polynomial satisfies our bounds on the coefficients. The coefficients, as well as it is positive and monotonic. But it's an expensive step, as we know. Also we can do some optimization to be able to basically try to pick some specific values. This can be modeled as a DMST problem. It's an NP-complete problem, but then there are some approximate solutions which we can get much efficient way, which we have not done, but then the older method itself actually gave us the right solution. The complexity of our attack comes to be so much. And then we did the implementation in Sage Math, and then we were able to, we actually enumerated, these are the random parameters that Sage Math picked for us. So we actually went through a bunch of alpha values and the beta values, and then the recovery time is mentioned here. The worst case is that in a few hours we were able to recover the polynomial as well as the input values. But remember, it's basically a family of the values, but then the family of the values is like far smaller than what is basically what they claimed that it's not possible in the paper. In this case, the degree of the polynomial was 9, and then we had about just 40 values that we could use and get these things. We also use real world data. This is basically from the UCI machine repository. It's basically a hospital data from a hospital in Venezuela, which is basically what was used in the KNN plus paper. In this case, the recovery was like far better because the alpha beta values were like far smaller. Future work, of course, we have to obviously make this is a full HE, the FHE setting probably will be much better than the SHE setting, and then develop alternate methods, maybe the ML methods, and maybe a combination of the ML as well as the FHE can be a better method to do these things for secure comparison and sorting. We thank Sonata for the funding, and then we also talked to the original or authors of the paper. It is in e-print, and this paper was accepted at IMACC last year in UK. Some acknowledgements. Thank you very much. Any questions?
So, if there are any questions you can take offline?